Hey everyone, you ever wonder how your computer or your phone can do all this amazing stuff when deep down it only understands two things, 0 and 1? It's kind of like they have their own secret language. Well, today we're going to crack that code. We're going on a journey to see exactly how these machines understand our commands.
So, here's our game plan. We're going to start with the absolute basics, like a computer's ABCs. Then, we'll see how those letters build up into a language. After that, we'll check out the grammar, the rule book that keeps it all in line. Then, we'll meet the little machine that actually reads the language. And finally, we'll see why any of this matters to you.
So this is the big question, isn't it? How do we go from simple zeros and ones to complex video games or spreadsheets? It seems kind of impossible. But the answer is actually in a really clever system of rules and super simple machines that turn these little symbols into powerful actions. And we're going to break it all down, step by step. All right, first things first. If you want to learn any language, you have to start with the alphabet, right? So let's get into the absolute most basic building blocks of how computers talk. Everything, and I really mean everything, starts right here with a symbol. You can just think of a symbol as a letter. For us, that's A, B, C. For a computer, it's usually just a 0 or a 1. They're like these tiny little Lego bricks. One brick isn't much, but they're what you use to build, well, anything.
So, what do you do with those symbols? Well, you group them up into an official set, and that's called an alphabet. It's basically the list of all the letters a computer is allowed to use. And for most computers, that alphabet is super simple, just 0, 1. That's the famous binary alphabet, and it's all a computer needs.
Okay, so we've got our letters, our alphabet. What's next? We start making words. And in the computer world, a word is called a string. It's literally just a sequence of symbols, one after another. So for alphabet is 0, 1, a string could be 101 or 00, or a longer one like 001001. So there you have it. It's really just a simple three-step recipe. You pick your symbols, you put them in a set to make an alphabet, and then you line them up to create strings. These are the computer's words. Simple as that.
All right, so we've made words or strings. But, a jumble of random words isn't a language, is it? You need some kind of rules to put it all together. And that's where this idea of a formal language comes in.
So, for a computer, a language is just a specific group of strings that are considered valid. A great way to think about it is like a super strict dictionary. If a string is in the dictionary, it's part of the language. If it's not, then it gets kicked out. Some of these dictionaries are pretty small, but some are, well, infinitely big.
Let's look at a few examples to make this real. Language 1, or L1, is a language of all words that are exactly 2 letters long. That's it. It's a small, finite language. But now look at L2 and L3. L2 includes every single string that starts with a 0, and L3 includes every string with an even number of zeros. These two languages are infinite. You could keep coming up with new words for them forever.
Okay, but wait a second. If a language can have an infinite number of words, you can't just write down a giant dictionary, right? You'd be writing forever. So we need a smarter way. We need a rule book, or what we call a grammar, that gives us a recipe to cook up all the valid words.
Now this is a huge difference you gotta get. The grammar you and I use for English cares about structure and meaning. The sentence, "The mouse wrote a poem," has perfect grammar, perfect structure, but it doesn't really make any sense. Computer grammars, they don't care about meaning at all. It's all about following the rules of the structure. A string like 0011 is either right or wrong based only on the recipe.
Let's actually walk through one of these recipes. So, we've got two simple rules here. Rule 1 says we can swap the letter S for ASB. Rule 2 says we can swap S for, well, nothing. So, we start with S. Let's apply Rule 1, now we have ASB. We can apply Rule 1 again to that S in the middle, which gives us AASBB. To finish it up, we use Rule 2 to get rid of that last S. And there you have it. We just generated a valid string, AABB.
So we have a language and a grammar to create words. But what if we need to do the opposite? How does a computer look at a word and figure out if it belongs to the language or not? Well, for that, you need a special kind of machine.
And here it is, our hero for this part, the automaton. You can think of it as a tiny, super focused little computer. It has one job: read a string, one letter at a time, and when it gets to the end, give it a big thumbs up, accept, or a thumbs down, reject. It's basically a grammar checker.
And what's really cool is how simple this machine's toolkit is. It has a bunch of states, which are kind of like rooms in a maze. It knows which room it has to start in, and it knows which rooms are the winning rooms. And most importantly, it has a map that tells it exactly which door to take to get to the next room based on the symbol it just read.
Now, there are two main flavors of these machines. The first kind, DFAs, are really strict. From any room, if it reads a letter, there is only one possible next room it can go to. It's like a train on a single track. The other kind, NFAs, are a bit more magical. They can explore multiple paths at the exact same time. But here's the really weird and amazing part. Even though NFAs seem way more powerful, they can't actually do anything a DFA can't. They have the exact same power in the end. It's a super important idea in computer science.
Okay, I know what you might be thinking. Symbols, grammars, abstract machines. This is all cool theory, but why does it matter to me? Well, it turns out this secret language and these little machines are quietly running the world all around us.
Seriously, this stuff is everywhere. You know the program that takes the code a developer writes and turns it into an app on your phone? That's built on these ideas. That find and replace feature you use in your documents, that's a tiny automata looking for a specific pattern. This theory is the absolute foundation for so much of the tech we rely on every single day.
And this isn't just a random pile of cool ideas, you know? There's a real structure to it. Brilliant people, like the famous linguist Noam Chomsky, actually organized all these languages and grammars into different levels of complexity. This gives us a roadmap for understanding what different kinds of machines are capable of. And that leaves us with one last really big thought to chew on. We've seen that we can build these incredibly complex languages from just a few simple rules, and then build machines that can understand them. But it really makes you wonder, what can't be described by these rules? What problems are so complicated that even our smartest machines can never, ever figure them out? That's the stuff that keeps computer scientists up at night. Thanks for watching.